Hello, good afternoon everyone. My name is Alejandro Morel and this webinar is about efficient indoor lighting. This webinar is the first of 3 about indoor lighting. Next one will be about energy efficiency actions and the last one will be about energy saving calculations. Today, first we're going to talk about general concepts, then some lighting parameters such as light measurement, and finally, we'll see different lighting technologies, luminaires, lamps, and auxiliary equipment. And we're going to compare these technologies from an efficiency point of view. As we can see in this slide, lighting energy consumption means almost 20% of all the electrical energy consumption in the world. In buildings, homes, offices, the importance of lighting rests in 2 factors. First one, depending on the building, of course, and climate, lighting usually represents from 20% to 50% of total energy consumption. Second, we can get significant savings with lighting renovation. We can see in the slide that with new lamps and control systems, the lighting consumption can be reduced up to 75 to 80%. Energy saving measures for indoor lighting are promoted by European Union. The 2012 Energy Efficiency Directive establishes a set of binding measures to help the EU reach its 20% energy efficiency target by 2020. Under this directive, all EU countries are required to use energy more efficiently at all stages of the energy chain, from its production to its final consumption. Also, energy-saving measures are promoted by EU members. Many countries have already established regulations related to energy efficiency for lighting. For example, Spain has defined energy efficiency requirements for lighting in the mandatory technical building code that applies for new construction buildings and rehabilitation projects. Okay, after this introduction, we're going to talk something about light and vision. Light color and the light reproduction of different colors will vary depending on the spectrum of each light source. In the left graphic, we can see the radiation chart of an incandescent lamp. These lamps, as the sunlight, have a continuous spectrum. This means when illuminated with an incandescent lamp, we can see perfectly the colors of an object. This also means that these lamps are less efficient because a great part of the light is emitted in the infrared range, and this light can be seen by our eyes. Lamps with this continuous spectrum, as we can see in the right chart, offer a light with less quality. This continuous spectrum have the fluorescent lamps and also the LED lamps. These lamps have a light with less quality, so we can note different colors as well. It's really important to take into account that when we talk about quality in lighting, this means our capacity to differentiate colors. But we will come back to this later. Glare. Glare may occur directly when we see a light source or indirectly if we see a specular surface. There are 2 types in terms of effects when we have glare. Psychological, for example in an office it's annoying, or physiological, while we are driving. Glare should always be avoided, and this justifies that we should not always illuminate the same way in every application. The most important thing about glare in energy consumption is that glare can justify higher energy consumption. First, because we must avoid or at least minimize direct daylight. Second, because we don't have to illuminate directly, we have to illuminate remote areas of the workspace, such as ceilings, walls, corners. And finally, we have to use diffractive elements in front of the light source, like diffusers. Following, we are going to talk about light measurement. When we measure the light, we can measure the quantity of the light, but also we can measure the quality of the light. In quantity, we can measure several things. First, we can measure the quantity of the light offered by a lamp. This is called luminous flux. Okay, here we're going to stop because it's really important to differentiate flux and power. The power is the electricity, the electrical energy absorbed by a lamp in watts. The flux is the capacity of the lamp in lumens. The rate between these two, between lumen and watts, is the energy efficiency of the lamp. We can also measure the amount of light that reaches a surface. This is called illuminance. The illuminance is measured in luxes. A lux is a lumen per square meter. These two, luminous flux and illuminance, are the most important quantitative measurements. But we can also measure the intensity of a lamp. This is measured in candles, and this is used in directional lamps, like LEDs. And finally, we can measure luminance without the I, luminance. But this is the light that a surface reflects. But this is more important in outdoor lighting. This graph illustrates all these measurements. We can see the power, the flux in lumens, as we said, the efficiency as the rate of lumens per watt. We can see the illuminance as the light that reaches the surface, and the luminance as the light the surface reflects. We also can measure, as we said, the quality. In lighting, quality means our capacity of seeing different colors. There is an index called Color Rendering Index, or CRI, that shows the quality of a lamp. This graph shows us how we see colors depending on the quality of the light. Sunlight, of course, has a perfect quality. The CRI of the sunlight is 100. This means we can differentiate colors perfectly when illuminated with sunlight. This also happens with incandescent lights, also have a CRI of 100. Fluorescent lamps and LEDs have a CRI of 80, maybe 90. In indoor, when we're talking about indoor lighting, CRI is always over 80. These two pictures we're going to see show how we see the same objects with different quality light. Here we have the objects illuminated with a CRI 80 light and a CRI 92. Let's go again. This is 80 and 92. We can see the colors better with a better quality light, of course. Finally, the correlated color temperature, or CCT, is the aspect the objects have in the light if the light is cold or warm. It's important to acknowledge that this is not a real temperature. If we say a lamp has 600 Kelvin, this doesn't mean that the lamp temperature is 6,000 or 600. Okay, this is just the color temperature or the light temperature. The higher the color temperature, the cooler the white light impression. This table shows the typical uses of different temperature lights. Let me draw your attention to the second row, cool white, 4,000 to 5,000 Kelvin. This improves blue color and it's a pale appearance. It's used for offices, hospitals, and factories. For example, if we see warm white, 2,700 to 3,000 K, it improves red and orange colors. It blackens blue colors. It is used for residential, restaurants, and hotels. Usually, we use warm light in residential facilities and cool light in offices, hospitals, and factories. We can see in these pictures how the same objects look when illuminated with different lights. The left picture is with a warm light, and the right picture is with a cool light. There are some studies about the effects of CCT, of light temperature, in workers or in humans. Here we find pictures of a Philips experiment. In this office, the illuminance and the CCT vary during the day to maximize worker performance. The conclusion of these studies is that the higher the illuminance, the higher must be the CCT. So when we have a great quantity or a high quantity of light, we need a cooler light. Okay, going further, after talking about these measurements, we're going to talk about lighting technologies. We're going to talk about luminaires, lamps, and auxiliary equipment. In the first picture, we can see a luminaire. The luminaire is the mechanism that distributes, filters, and transforms the light emitted by one or more lamps. Also, the luminaire protects and prevents lamps glare. The lamp is the key system, is the main source of artificial light. The lamp basic function is to generate light by converting electrical energy. Not all lamps work by themselves. Some of them need auxiliary equipment, like ballast or transformers. The ballast is the electrical equipment needed in some lamps for igniting or maintaining the luminous intensity. And finally, the control system, the last picture, is the set of mechanisms to turn on, turn off, and regulate the luminous flux produced by lamps. About luminaires, we can differentiate luminaires by the kind of light they give. The most common or the most typical luminaire would be the direct luminaire, when the light is directed through the work surface. This is the most efficient luminaire, but we can have the problem of glare. So we have indirect luminaires when light goes in the opposite direction than the working surface. Between these two, direct or indirect luminaires, we have some other options: semi-direct, direct-indirect, semi-indirect, and general diffuse. We can see all of them in the chart. Also, we can classify luminaires depending on how they're mounted. We have surface-mounted, downlights, suspended luminaires, projectors, wall-mounted luminaires. When we're going to choose a luminaire, we have to consider first our lighting needs, our quantity and our quality required. Then the efficiency. The efficiency of a luminaire or light output ratio is the light we get from the luminaire compared with the light we get from the lamp. We're going to talk about this later. Then we have to consider protection, but this is more important in outdoor lighting. The luminaire has to protect the lamp. And finally, of course, the cost of the luminaire, the cost of the material, the installation, and also the maintenance. About efficiency, as we said, we define luminaire efficiency as the rate between the flux emitted by the luminaire and the flux emitted by the lamp. This is called light output ratio, LOR. The closer the LOR is to 1, the better. This means that the luminaire is more efficient. Usually, most luminaires have a LOR around 75, 80, 85%. Following, we are going to talk about lamps. As we said, lamp is the most important equipment because it's the lamp that generates the light. As we said, the lamp is the equipment that converts electricity in light. We find different ways of getting this light. The most common are Combustion or incandescence, we get the light when a body reaches a certain temperature. The natural example of combustion would be the sun, and the artificial example would be an incandescent lamp. Another way would be the gas discharge. We get the light when a current goes through a gas. For example, in nature, we find this when comes a ray. In artificial world, we have the discharge or fluorescent lamps. And finally, the solid-state lighting, the radiation, like in a glowworm or the LED lamps. So these are the three main families of lamps: incandescent lamps, discharge lamps, and solid-state lighting. All the lamps we use belong to one of these families. In incandescent lamp family, we have the non-halogens incandescent lamps and high and low voltage halogens. We use incandescent lamps in homes, at homes, in living rooms, etc. Discharge lamps, the second family, the only discharge lamp we use in indoor lighting are fluorescent. Fluorescent is low pressure mercury. All the other discharge lamps are used in outdoor lighting: high pressure mercury, metal halide, and sodium. Those are used in outdoor lighting. Only fluorescent is used in indoor lighting. And finally, the third family would be LEDs, light emitting diodes, and organic LEDs that are used especially for TVs. We have, of course, other technologies, other lighting technologies, but those are less common. We have LEP, light emitting plasma, and ESL, electron stimulated luminescence. In recent years, the lighting world has experienced a revolution. This has been provoked by the arrival of LED lighting. Let's analyze this technology further. First, what's a LED? A LED is a diode composed of several layers of semiconductor material that emits light when it is correctly polarized through the path of electric current. This diode and its electrical circuit are encapsulated in a plastic package. The advantages of LEDs are basically two. First, high efficiency. Second, high lifetime. So the applications, the uses are traffic light systems, decorative lighting, signs and neon, and of course, indoor and street lighting. Other considerations with LED technology is that light color is different depending on the materials used. The blue LED is the most efficient in lumens per watt, while the white LED is the less efficient. The white light production can be in two ways. First, a blue LED and a yellow converter. Second, the combination of red, green, and blue LED. Finally, the last consideration with LED is that LED systems emit in a localized way. The maximum emission angle is about 120 degrees. This is an advantage because we find a more efficient system with direct light, but this is also an inconvenience because we can have the problem of glare. This graph shows the components of a LED light. First, at the right, we see the power source. These lamps cannot work by themselves. They need a power source to obtain the desired voltage and the desired current. Then we have the heat dissipator. The key factor in LED lighting is the heat dissipator. We're going to talk about this later. Then we have the PCB and of course the diode, the LED. And finally, we have the optics. Importance of heat dissipation. As we said, in LEDs, the most important thing we have to consider is the heat dissipation. LEDs don't radiate energy, so we have to dissipate the heat in other ways. This table shows the comparison between different technologies. We have incandescent, fluorescent, metal halide, and LEDs. Let's focus in the first row, the visible light. Incandescent, the 8% of the energy is visible light. These lamps are not efficient. LEDs, the visible light is 20 to 30%. But if we see the total radiant energy, visible light plus IR plus UV, the total radiant energy in an incandescent is 81%. In a fluorescent is 58%, but in LEDs is only 20 to 30%. So the rest of the energy, the 70 to 80% of the energy, has to be dissipated in conduction or convection. That's why it's so important, the heat dissipation. Because if we don't dissipate this heat, the temperature of LEDs become too high and the LED performance is lower. LED performance means efficiency and lifetime. So if the temperature becomes too high, the efficiency is lower and the lifetime is lower. So when we're choosing a lamp, there are four criteria we have to take into account. First, like in luminaires, the lighting needs quantity and quality. We're not going to use the same lamp in a bedroom, a living room, a bathroom, or a library. So we have to set our needs, and then we can choose the lamp. Of course, we have to consider the efficiency. We said the efficiency in lamps is the capacity in lumens compared with the power in watts. Of course, we have to consider also the lifetime of the lamp, the duration, the years of duration of the lamp. And finally, the cost of the material, the cost of the lamp, the cost of the installation, and also the maintenance. We said the efficiency, the lamp efficiency is the rate between the lamp capacity in lumens and the lamp power in watts. The lamp efficiency depends, of course, by the type of lamp, the kind of lamp. We can see an incandescent lamp has an efficiency of 12 lumens per watt. A fluorescent lamp has an efficiency of 80 to 82 lumens per watt. A LED has an efficiency of 85 lumens per watt. Of course, the lamp efficiency considers the input energy lost as heat. Finally, after luminaires and lamps, we're going to talk about auxiliary equipment. Not all lamps work by themselves. Most of the lamps need auxiliary equipment to work. Fluorescent lamps need ballast, for example. The ballast is the equipment that limits the current of the lamp, creates the startup power peak, and corrects the power factor. Also, halogen incandescent, low tension halogen incandescent need transformers to work. The transformer transforms to low voltage and protects the lamp from overloads. Also, LEDs need transformers. In LEDs, we usually call the transformer the driver. The driver transforms to low voltage, protects the lamp from overloads, and also regulates the flux and the power of the lamp. When we're talking about energy consumption of the indoor lighting, we have to consider not only the energy consumed by the lamp, but also the energy consumption of the auxiliary equipment. Ballast and transformers also are an energy consumer. The energy consumption can be measured or be obtained of technical specification, but usually we estimate the energy of the auxiliary equipment knowing the power of the lamp and the kind of lamp we are working with. For example, this table shows that electromagnetic ballasts have a power of 20 to 25% the lamp power. The LED drivers have a power of 5 to 15% the lamp power. Other considerations of auxiliary equipment is that the lifetime of auxiliary equipment may be less than the lifetime of the lamp. So this auxiliary equipment, this ballast or this transformer should be easily accessible. The stability of auxiliary equipment, voltage, current, and power factor, is essential to optimize the luminous flux, power, color, and lifetime of the lamps. This is especially important in LEDs. In LEDs, one of the key factors is the stability of the auxiliary equipment. We need a good voltage and a good current, and a stable voltage and a stable current to get a good performance of LEDs. Finally, if the auxiliary equipment allows adjustment of the lamp, this is called dimming, the performance, the efficiency of the lamp can be maximized. This table shows a comparison between all lamp technologies. We have incandescent, halogen, fluorescence, and LEDs. And we can compare the efficiency, the power, the waste management, the auxiliary equipment, the quality, or CRI, the application, the lifetime, CCT, or color temperature, and finally, the regulation. We said the main advantages of LEDs were efficiency. We can see that the LED efficiency is the highest. And also the lifetime. We can see that the lifetime of LEDs is up to 80,000 hours. But if we compare CRI, the quality, we said that incandescent and halogens are the most interesting lamps. Okay, so we choose the lamp depending on our requirements, on our quality and quantity needed. Finally, the power consumption of a lighting system is equal to the system power multiplied by the time of use. First, when we want to set the energy consumption, we have to determine the power of the system. The power of the system would be the power of the lamps plus the power of the auxiliary equipment, the power of the ballast, the power of the transformers. Once we've set the power of the system, we determine the energy consumption with the second formula. The energy consumption is the power of the system times the time of use of the system. Next week, in the next webinar, we're going to start with this formula, and we're going to see that the only ways to reduce the energy consumption are, first, reduce the power, and second, reduce the time of use of the lighting. So, thank you all for your attention.